Good morning, ladies and gentlemen. Welcome to this very quick video on sampling distributions. This is just an introduction to get some notes down so then we can start some of the more basic questions. Essentially, a sampling distribution is a sum of random variables. So if we have random variable x, there is a sum of observations that look like this, Sn, where n is the number of observations. So a very easy way to think of this is rolling a dice. If we roll one dice, it has a mean of 3.5 and a standard deviation of 1.78. If we roll 10 dice, then we would expect the mean to now be 35. And that's what this says here. Whoop, that's not at all close. In that the mean of the result, so this here is saying the mean of the sum is n times the mean of each individual one. So if we're rolling 20 dice, we're thinking mean of 70. Standard deviation is a little more complex. It's the original standard deviation multiplied by root n. And we'll look at why it's root n in investigation in the textbook. It can be seen fairly simply, but it needs a bit of spreadsheet work, which we're not going to do here. Alright, so a very simple example might be a random variable x has mean of 10 and standard deviation of 2. Find mean and standard deviation S9. So that's the sum of 9 of them. Mean, very simply. Standard deviation, also fairly simple. Alright, and a typical question might look like this. If let x be the duration of songs on Corey's playlist, x has a mean of 3 minutes, standard deviation of 0.5. What random variable describes the time to play 16 songs? Well, it's S16, which is basically the sum of 16 songs. And the mean is going to be 16 times 3. And standard deviation is going to be 3 times root 16, which works out quite nicely, is 12. And what's 3 16s? 48-ish. My mental arithmetic should be better than that. Alright, so those two formulas up there are very useful when it comes to sum of distributions. Now, this is subtly different. A sample mean. So let's say we take that sample of 10 dice before. The sample of 10 dice before, we know that the sum of the distribution should be n times the distribution of each individual one, or 3.5. Also, for n independent random distribution, the mean of the observations in the random variable is, so here what we're talking about is not the sum, or not the average sum of the distribution, but given we've got 10 dice we've rolled, what is the average of each dice? And it shouldn't surprise us that if we roll 10 dice and take the average of each dice, meaning we add the outcomes together and divide by n, if we add the outcomes together and divide by n, then we still get a mean of 3.5. However, what we should find is that the standard deviation is much lower for the sample distribution mean. And the important formula to remember is this, is that if we're looking at distribution of sample means xn, the mean doesn't change, but as the distribution gets larger and larger and larger, the standard deviation away from the mean gets lower and lower and lower. And I guess a good conceptual way to explain that would be, let's take several different dice rolls. Several different dice rolls, if we just roll one dice, we get values from 1 to 6. If I roll 10 dice, then I get values from 10 to 60. But let's say I roll 10 dice, and what this is asking me to find is then find the mean of those 10 dice. The mean of these 10 dice will be 3.5. And then the standard deviation of that mean, well, this here, from just one dice roll can go anywhere from 1 to 6, and they're all equally likely. However, with 10 dice, the mean of each dice is 3.5, and because there's so many scattered around, on average, because we're rolling 10, it's going to be quite close to 3.5 there, whereas here it'll be anywhere from 1 to 6 will be the mean of that distribution, because it's n equals 1. So what's happening here is as we add more and more and more dice in, the mean of our distribution will get closer and closer to 3.5. So if we roll 1 dice, yes, the theoretical average is 3.5, but we'll never actually get to 3.5 because we'll either might roll a 3 or 4 or 5 or a 6, etc. And that's why our standard deviation is quite high. If we roll 10 dice, we're quite likely to get closer to the 3.5 because the averages will balance each other out. And that's why this portion here is a lower standard deviation. That's why we're dividing by root n. If I roll 200 dice, the average of my 200 dice is going to be almost exactly 3.5. And once again, we'll look at this in the textbook. And there is some algebra to prove it. Essentially what happens as we increase the number in each sample, as n increases, the standard deviation shrinks towards about the mean. And that's something that SACE is very keen on you being able to recognize, is that as the sample size increases, it gets increasingly close to the sample mean, and if the original distribution was skewed, as in looked a bit like that, it's a terrible example, if the original distribution looked like that, then as we go to higher and higher, it will look more and more normal, about the same mean. Alright, I hope that made some sense, and if it didn't, I hope you got the notes down and you're ready to ask questions in class. Thank you very much.